Okay, what you're looking at there is the SWeir designed um, essentially the Q1 oscillator portion with precision current sense resistor and properly constructed ground planes and an IRF PG50 MOSFET in there. And here I'm looking at the voltage across the current sense resistor with this this special probe master probe connector there. That is a minimum inductance probe connection, and this is what the current trace looks like. That's where the zero baseline is, right there. And we are looking at that at 1/10 of a volt per division. Okay, and so I'm seeing 1, 2, 3, 4, 5, just a slight hair over 5/10 of a volt, but it's got rounded shoulders. So if you cut off that 5/10 of a volt, the top area there, and then fill in the shoulders there, you're probably going to wind up with about 4.5, or rather 0.45 volts of drop across the 0.25 ohm current giving resistor. And as you can see, I've got the display set so that, and the duty cycle set so that the on time is 1/3 of the period. Right, so we got 1, 2, 3 full divisions for the period there. And this is happening at a frequency of 164 kilohertz, 164.4, driven by the function generator this time, to give a nice square-ish kind of pulse. Okay, so what did we say here about 0.45? So let's do the math. Let's see, 0.45 divided by 0.25 is 1.8 times the duty cycle 0.33 is 594 milliamps, and the inline meter is indicating say 565 milliamps because it's flicking to the 570 there. So 570 against 594, so we're very, very close, and the error is because of the insufficient estimation of squaring off this pulse here. Let's say if we called it 0.44 volts, 0.44 divided by 0.25 is 1.76 times 0.33 duty cycle, and that's 0.58 amps against 0.56 or 57 amps. So in terms of getting the average current across that cycle, the old DMM is in very close agreement with the computation of the current, average current, measured by the most sophisticated means that I have available, which is the SWeir designed current monitoring and voltage monitoring board there. I also have a place where I can monitor the battery voltage and all the other parameters of the Ainslie Q1 circuit, and then I can also hook up some Q2 MOSFET or two in there to make the full Ainslie circuit with this precision current monitoring setup, thanks to SWeir. Okay, now I have the VBatt probe in there as well. So we have the input current and the battery voltage being monitored from the board. Here's what the traces look like. This is where the zero baselines are. This is the current trace down here. This will be at 0.5 volt per division. There. And you can see we've got a 30%, or rather a 1/3 on, 33% on duty cycle, and half a volt per division. So we're looking at around, well, we'll say 0.45, 0.44 volts there across the 0.25 ohm current giving resistor, and we're operating at a voltage of about 24-25 volts. And you can see that there's very, very slight ripple there. So let's see just exactly what that ripple is. Just switch to AC coupled here, and then go to 1 volt per division. Where's the baseline? There it is. Okay, so at 1 volt per division, you can see that we have somewhat, just about exactly 1 volt peak to peak of the ripple sitting on top of that 25 volt signal. So that's about 4% ripple, something like that, if I'm doing the math right. Okay, so let's go back to DC coupling and get the trace back on the screen at 20 volts per division. There's our baseline, and there's the current trace and the voltage trace. So the voltage is essentially constant across there. So I think we can justify taking the average current, multiplying it by the voltage, and saying that that's our average input power. Okay, and right now I have a test running, actually. That's what the meters say, and that actually agrees with the computation from there. And I'm recording the temperature with the camera and the intervalometer, and we will be comparing this to the other systems that I've tested. And once again, I want to thank SWeir for his careful and precise work on this shifted paradigm instrument board. It's very versatile. I've already tried it with a Q2 hooked up, and it does produce oscillations, Q2 oscillations. It's a pretty neat little gadget. Thank you for watching.